condition, easy. So we're doing this under basic conditions using sodium hydroxide as our strong base, and we're also using H2O and H plus as our catalyst, so we just have enough to do this reaction. So sodium hydroxide will dissolve into Na plus and OH minus in solution, and we will use hydroxide to abstract the alpha hydrogen HA here, and this will form a double bond, pushing the carbonyl electrons up, forming an enolate, and we have resonance character here, so we can push the electrons back down from the oxygen and push these electrons on the carbon to make this. And since we have more aldehyde in solution, we can use this nucleophilic carbon that's negatively charged to attack the carbon double bonded to the oxygen, and we have to push these electrons up so it doesn't have more than 4 bonds. And you should get this structure. And here's the hydrogen that I did not draw in for simplicity. So you see we have 1, 2, 3, 4, 2 from each. And now through our catalyst up here, H2O and H plus, they will combine to form H3O plus. Actually, let me draw it fully bonded. This oxygen here is going to attract that hydrogen. We're going to get back the electrons, and we will get plus water. Addition, except we're doing it under acidic conditions this time instead of basic. So what will happen first is this oxygen is going to take this hydrogen from the hydronium, and that'll push these electrons back. And what we'll get is this, and this will put a positive formal charge on the oxygen since we have 3 bonds, which will also form water as a byproduct. And that's important because now we have this alpha hydrogen here, and we can abstract the alpha hydrogen, which will form a double bond, pushing these electrons, the pi electrons, back up, and we'll make this. Well, now we have an enol, not an enolate since there's no negative charge on the oxygen. It's an enol since we have hydrogen. Sorry, since we have a hydroxy group. And assuming we have another aldehyde, which we do, we can attack this. But before we attack, we have to protonate this oxygen right here. And we can do so with another hydronium. And the reason you have to protonate it is because since enol is a much weaker nucleophile than enolate, we have to make this carbon right here more electrophilic. So it's more of a weaker target, making our nucleophile appear stronger than it actually is. So that's why you have to protonate the second aldehyde. And now that it's protonated, we can do this in a single step using the double bond electrons, and we can make our structure. So we have 4 electrons. You also have to push this down, push that back up, and you get this. And it's the same as before. You get 4 carbons, and then you put the hydrogen at the end. And we're almost done. We want a neutral atom now with the positive charge. So we're going to use water, our solvent. We're assuming it's our solvent. It usually will be, to abstract this hydrogen, which will push the electrons back. And this in turn will make this, which is the exact same product as we got in the last video. Let's do a retro-aldol reaction. A retro-aldol reaction is just the reverse of an aldol addition. So you need a strong base, and you need to put it in an aqueous medium like water. So what's going to happen is this hydroxide group right here, it's going to abstract this OH's hydrogen, and this will return the electrons, and what you get is this. You get this O minus. And now what you can do is, since you have this extra lone pair, you can bring down these electrons. But then also, since this is reversible, you can break this double bond you can break this bond here that was formed between the these are two aldehydes. And you can break this bond here by returning the electrons back to the original enolate. So we're going to do that. We're going to make a double bond, and then we're going to push these electrons up so the carbonyl does not go above 5 bonds. Sorry, go above 4. So what you get is this. Plus, you get this. So this aldehyde is done. We got one aldehyde. Now we just have to fix this. Now we have our enolate, and we want to convert it back into the aldehyde. And what you're going to do is you're going to use the water that we have, since water is our solvent, and you're going to donate, and you're going to donate your hydrogen back to the original methyl group. And then you can push these electrons back down, and what you get is this, and I'll draw the methyl group just for reference. And you get this. You get your 2 aldehydes back. And then you also reform the hydroxide ion. This is a dehydration reaction. And to get this product, you first need to go under Aldol addition. Sorry. And this molecule is called alpha beta hydroxyaldehyde. And it's called alpha beta because our key components of this reaction involve this alpha bond, right? This alpha carbon, and this hydroxyl group, which is on the beta carbon, away from the carbonyl. I just wanted to say that just so you know how these names are actually made, because sometimes it's quite confusing. So how this reaction is going to start is, this is a dehydration reaction, means it's going to produce water, and the only way we can produce water is through this hydroxyl group. But this hydroxyl group cannot leave on its own, because if it leaves, it becomes OH minus, and good leaving groups are weak bases, and OH minus is a strong base. So what we have to do is, since we have H2O and H plus, a catalyst, they're going to combine to form hydronium, and then we can use, and this oxygen is going to abstract the hydrogen from the hydronium, and it's going to protonate into this. And now we have a good leaving group, because water is a good leaving group, because it's not a relatively strong base. It's a relatively weak base. So now that's going to leave, and at the same time, since we just formed another water molecule, since we abstracted that proton from hydronium, it's going to take this alpha hydrogen from the alpha carbon, and then we're going to form a double bond here. And I'm going to write it all the way down here. And what you get is this. You get alpha beta unsaturated. And it's unsaturated because of the double bond we have, because it's not fully saturated with the maximum amount of carbons it could have. And if you're questioning why we have this little delta sign here, that's a way to show that we have added heat to this reaction. And since this is an elimination reaction, you need to add heat, because elimination reactions typically have high activation energy. So it's an endothermic reaction. So you need to add heat in order to have this reaction spontaneously react. Thank you for watching.